Okay, welcome to the binomial expansion. A couple of examples will be coming up soon, but let's talk about a little bit of theory first. The binomial theorem from your formula booklet looks rather abstractly and quite intimidatingly like this here. And here's a second formula. So let's try to get inside of this a little bit better and more quickly, just considering quite literally a binomial, namely a plus b, as it's expanded. So a plus b squared, as you know from the FOIL method, is just a squared plus 2ab plus b squared. I've highlighted the ones here. So you see a 1, 2, 1 arrangement. A plus b, this binomial cubed, which of course would be a plus b times a plus b times a plus b. If you took all of the time to work that out, you would see that you get a cubed plus 3a squared b plus 3ab squared plus b cubed. You get the idea. So notice what's happening. You've got a 3, 2, 1, and of course hiding in here is a to the 0, and you know that any number raised to the 0 power is 1, so it's not there. And working backwards, you've got b cubed, b squared, b to the first, and hiding in there is b to the 0. So there's a pattern that's starting to emerge, and this 1, 3, 3, 1 has a relationship to the 1, 2, 1, and we'll see that in a few seconds. A plus b, this binomial expanded to the 4th power, you get, again, the 4, 3, 2, 1, 0 on the a's, while the b's work backwards in terms of 0, b to the first, b squared, b to the third, b to the 4th, and a 1, 4, 6, 4, 1 arrangement. So there is something happening here pattern-wise, and it does relate to both of these formula that we'll see here in a few seconds. And so there is something called Pascal's triangle, right? And so here's a formation of Pascal's triangle. You start off with a 1, you write down a 1 and a 1 again, and then you write down a 1, and then 1 plus 1 makes 2, and then you carry down with a 1. And then you start with a 1 again, and then 1 plus 2 makes 3, and then 2 plus 1 makes 3, and you write down the 1 again. And you see the pattern. Write down the 1, and then 1 plus 3 makes 4, 3 plus 3 makes 6, 3 plus 1 is 4. You get the idea, it unfolds. And these numbers that are showing up, they are not accidentally the 1, 3, 3, 1 you see here in this cubic binomial expansion. Here's a 4th power, the 1, 4, 6, 4, 1, that's right here. And of course the next row would be 1 carried down, and then 1 plus 4 makes 5, 4 plus 6 makes 10, 6 plus 4 makes 10, 4 plus 1 makes 5, and carry down to 1 again. So there's a pattern unfolding. And if you back up, of course, a plus b to the 1st power is just 1a plus 1b. And further, a plus b to the 0th power, any number raised to the 0 power is just the 1 to get things started. So things are starting to come together a little bit, hopefully. So you have in your GDCs under math, and if you scroll across to the probability sub-feature, you've got this sort of number of ways of combining R elements out of n, which is what that stands for. So you can start to generate the number of ways to combine 0, 1, 2, 3, 4, and 5 out of 5 as a total. And you start to see these numbers showing up. So what's happening? So these values that you can confirm from your GDC start to relate, for starters, to this guy here. So this is describing the number of ways we can combine R elements out of n total. And it's got this factorial concept embedded within it. So the number of ways we can combine 2 out of 5, which the GDC gives you as 10, which comes from, again, that Pascal's triangle arrangement, you end up getting n of 5 factorial over r of 2 factorial, 5 minus 2 factorial. What is a factorial? That just means 5 times 4 times 3 times 2 times 1. You don't need to take it all the way down, because once you get 3 factorial here, which of course means 3 times 2 times 1, you can just say, if you had like a paper 1 context, that 5 times 4 times 3 factorial is the best way to think about that, because these guys would cancel. And then, as it turns out, 20 over 2 accounts for your 10. So it ties together. These numbers that were provided by Pascal's triangle, as Pascal's triangle unfolded for us, right? These numbers are exactly these coefficients that are falling out of this binomial expansion, and that's why you see these elements positioned here. So we're going to look more closely at that very, very general abstract representation in a few seconds with an example. So let's do a typical sort of binomial expansion which contains some term that's the x cubed y squared term with some coefficient in front called k. Let's find k. Well, you could crank out a plus b raised to the 5th power as some side work and do a lot of fancy multiplication, take a lot of time. You would end up getting this. Well, this is provided by a plus b to the 5th power by this guy here. And you can actually also get it by just saying, well, I know that Pascal's triangle provides very quickly this row, which relates to the coefficients. And then you can just say, well, if that's the case, my 1, 5, 10, 10, 5, 1 has to start off with an a to the 5th, which works down to the 4th, to the 3rd, to the 2nd, to the 1st, to the 0. All the b's work backwards. Well, if you look more closely at just this very general expansion of this binomial and say, well, really my a is 2x and my b is 3y, then I need really a to the 5th. Well, there it is, plus b in here times a to the 4th with a 5 coefficient. You can see things unfolding. You don't need to go any further because we're trying to figure out the coefficient, if you will, on the x cubed y squared term. And that ends up just keying on this piece right here, which actually relates to be generalized right here. We'll see in a few seconds. So I need 10 times my a, which of course is 2x raised to the 3rd power, times my b, which in this context is 3y as a term squared. And then when you work out the algebra on this, of course, each of these squared is right here, each of these squared is right here, and just here's 8, here's 9, and so as it turns out, we need 720. And so that ends up being, this term right here, ends up just being the number of ways we can combine, as it turns out. We've got 0, 1, so 2, so it looks like r is 2, and n is 5, and you can see that this would actually give you exactly what you see here to get you right to the heart of that answer of 720. Another example, IB can make it look a little bit more abstract. What about taking something like this raised to the 9th power? Now they've blocked you out from actually doing the long sort of Pascal's triangle and really building yourself all the way down to that row that's got the 9 in there. So a couple of things going on here would be for you to say, well, okay, this looks rather menacing, but they're really just saying, given that it can be expanded to look like this, so here's your sort of x to the 9th, x to the 8th, x to the 7th, x to the 6th term, and then you got y to the 0 embedded in there. Here's y to the 1st, y to the 2nd, y to the 3rd. So they're really just saying, hey, what is this coefficient value right here? One feature of this worth noting is that whenever you have a binomial where there's a minus sign, you're recommended to treat it as the addition of the negative. So then your a clearly becomes this guy here, and your b is a negative term. And so basically what you need is you've got 0, 1, 2, 3, right? Your r is 3. So the number of ways you can combine 3 out of 9 from that formula times, so this a value to the 9 minus 3, which is where that's coming from, times your b to the actual rth power, which in this case is 3. And so you're really just cutting right to the chase of how those algorithms or those formulae are helping you. This guy comes from your GDC. He's 84. 2 to the 6th, x to the 6th is going to be falling out of there. And then negative 3 cubed is going to account for negative 27. And so all of this on a GDC gives you this massive number here. And so it looks like A needs to be 145,152. Okay, lastly, classic example is when you've got some kind of fractions involved, can you actually get the constant term? So to help visualize what's going on, if you were to raise this binomial, right, some a plus b to the 6th, if you were to sort of play that out, here is your a to the 6th, and then Pascal's triangle, or that formula, gives you There's 6 ways to combine to get, actually here's your a to the 5th times b to the 1st, and you get the idea. And so the question is, like, what's happening? So here's going to be x to the 10th power, and that's going to be divided by x squared. That still leaves me with a variable term. Here's x to the 8th power going to be divided by x to the 4th. Well, that's still a variable term. Here's your magic moment, because you've got x to the 6th power divided by, x to the 6th power, because of course power is the power as you multiply those exponents. So these guys will undo each other and leave you with just the constant term. And you can see it down here. So I need the 20, I need this a value cubed, which in more detail is of course 27x to the 6th. And then this b value cubed looks like it wants to be 2 cubed, which is 8 over x to the 6th. These guys undo each other, and you get that the constant term, namely the term without a variable, will be 532. That's it. Thank you.